Hi, my name is Drew Griffiths, and this is my presentation for Physics 2212, Lab 3, Macroscopic View of RC and DC Circuits. Well, the purpose of this lab is to use the loop rule and the charge conservation and definition of the steady state to predict the behavior of circuits containing resistors in series and parallel, and then also use multimeters to measure the actual values of the conventional current and potential differences in the current, and examine the behavior of the ohmic resistors and capacitors. And here on the left, you can see two diagrams of the two experiments that we performed in this lab. And a sneak peek of the results, the node and loop rule was proven true, and so was Ohm's law, which is consistent with the physics and the result we were trying to prove in this lab. And here are the fundamental physical principles that were used in this lab. First is Ohm's law, and it is equal to the voltage is equal to the current times the resistance. And then the loop rule, which is summing up all of the potential differences, that is equal to 0 because of path independence. Sum of all voltage slash potential differences in a closed loop is 0 because the energy and the charge is conserved within the system. And this is the same for the node rule, where the charge in and the current in is equal to the current out because of the energy is conserved. And here's a little bit of information about our two experiments. So the system in this experiment was, or in both experiments, was the circuit and all of its components, such as resistors, capacitors, batteries, etc. And the surroundings were everything else, like everything in the room, the table, all that stuff. And the experiment details, we recreated the experiments detailed in the lab document. Batteries and capacitors were put in series, and then experiment 2 analyzed the charging and discharging of a capacitor over time using an RC circuit. All right, here is the experiment 1 information. So on the left here we have the initial conditions, where the total resistance is 145 ohms, which is calculated by adding the resistance of the 100 ohm resistor and the 45 ohm resistor. And using Ohm's law, we determined the current to be 0.0207 amps. And here's a picture of our results down here in the bottom left. A diagram of the experiment. And then our post findings for this experiment was that the potential difference across the 47 ohm resistor was negative 0.97 volts. Across the 100 ohm resistor, it was negative 2 volts. And the total delta V across the loop is 0.1 volts. And this could be because of multiple errors that I will discuss later in these slides. And here is a graph of the potential for this experiment. And here are the results for experiment number 2, the RC circuit. And then when charging and discharging the capacitor with the 5.5 volt light bulb, as you can see here, the results were very similar, 51 and 50 seconds. And then for the 1.6 volt light bulb, it was 10 seconds and 9 seconds. And these results are not impacted by the voltmeter because it has a very high resistance and negligible current flows through it. The observed versus predicted results for this graph. So the similarities was that the current was the same throughout the circuit in both the observed and predicted model. And this means that the loop rule was satisfied and the voltage prediction was the same as our calculation. And the difference were that the pre-calculations used background formulas had small differences due to minimal resistance in the wires and the batteries that is not accounted for in the ideal formulas we used. And some human errors were also present, which caused some deviation in our results. The human errors that I discussed in this last slide were delay in human reflex time / vision of seeing when the light bulb went out in experiment 2, leading to some possibly small inaccurate discrepancies in the time of the charging and discharging. And then, like I mentioned in the last slide, the equipment used was not fully ideal, leading to some variation in the results. For the conclusion, what if you had a charged capacitor with no resistor in the circuit? How quickly would the ideal model predict the capacitor to reach full charge? With no resistors, our model would predict that the capacitor would be charged almost instantly. Resistance from the wire and internal resistance from the batteries would be the only resistance slowing down the charge of the capacitor. So it would be very quickly, almost instant. And that's it. So thank you for watching.